Okay, so in part two of this video series, now we're going to be talking about the adiabatic reversibility of a gas that is expanding as it is moving up, or not expanding, but increasing in volume as it goes up higher in altitude. So let's say we have it in state one and state two. We have a gas in that's expanding as it's going up. And we're going to be talking about this in terms of the first law of thermodynamics, which is this one right here. The change in internal energy is equal to the change in heat on the system minus the work done on the system. Now, in terms of an ideal gas, which is what we were talking about, this work is equal to the pressure multiplied by the change in volume. So from here, since it is reversible, we can just say that the external pressure of the system, so the pressure going on the outside of the system right here, and the pressure that's inside of here are equal to each other. So we're just going to keep the pressure just denoted as P, because no matter if we're talking about external or internal, it's going to be the same value. And then with it being adiabatic as well, that means we're putting in or taking out no heat. So we're not putting in or taking out heat from the system at all. So then from there, we just have the change in internal energy is just equal to negative P dV. But we can also say, since from here, since we're not adding any temperature or anything like that, this is only affected by temperature. So we can also rewrite this as du is equal to the specific heat multiplied by the change in temperature. So that means that the specific heat multiplied by the change in temperature is also equal to negative P dV. So the pressure times the change in volume. But we do not want to denote this in terms of pressure. What we can actually do is, from the ideal gas law, is we can set P equal to RT over V, and then notice we don't have the number of moles in there because we're just going to assume that the number of moles is 1. So then from here, we can set negative RT over V, and then notice we're still multiplying by the dV is equal to the specific heat multiplied by the change in temperature. And then from here, what we can actually do is we're going to want to integrate this, but as of right now, it's not that easy to integrate, so we're going to do some algebra. So if we move the t to the other side, move the t to the other side, and then keep everything else the same. So this becomes negative r, and then just so we can see this easier, this becomes dv over v is equal to the specific heat times the change in temperature over the temperature itself. So then now, if we integrate this, we'll just get the natural logs for this, but what we're worried about is the limits of integration on these. And from what we're doing it from one temperature to the other. So the temperature up here at 1 and the temperature at 2. So if we integrate this, so we do this, wiggle. So we do it from T1 to T2, volume 1, volume 2. And then what we're going to get is, after doing that, so negative R, and then the natural log of V2 minus the natural log at V1 is equal to the specific heat, natural log at T2 minus natural log at T1. And then since the definition of subtracting those two, then it will become negative R natural log of V2 over V1 is equal to the specific heat multiplied by the natural log of temperature 2 over temperature 1. And then from there, it just makes things a lot more simple to do. And then we can also move the specific heat to the other side. So if we just rearrange this, so we'll say that the natural log of temperature 2 over temperature 1 is equal to negative R over the specific heat times the natural log of the volumes. And then the other definition of this is we can take the gas constant and the specific heat, and since it's multiplied by a natural log, it'll just go into the exponent. So then we can take this, and then after that, we'll simplify from here to more. We can take e to the natural logs just to get rid of these. So then this becomes T2 over T1 is equal to volume 2 over volume 1, and then mess that up right there, to the negative R CV. So here we've kind of derived the expression a little bit more, but we want to do this in terms of temperature and pressure instead of volume. So again, we can morph the ideal gas law and say that our volume is equal to, RT over P, and then actually I wrote that up there as well, I believe. In other forms. So now what we can do, and we can just substitute them in for volume 1 and volume 2. Okay, so then if we plug in if we bring this back down here, so temperature 2 over temperature 1, and if we get rid of the volumes and we plug it in with the gas constant and then the temperature over the pressure, we can plug those in for volume 2 and volume 1. The R's will cancel out, so then it'll end up being the T2 over pressure 2, and then multiplied with P1 over temperature 1, and then that's to the negative R over the specific heat. And then we can multiply by the reciprocal of the exponent with the temperatures. So then we can get temperature 2 over temperature 1 is equal to, and then the temperatures will cancel out, so that would be just P1 over P2. And then that will just be to the R over CV. And then this will become 1 plus R over CV. And then from there, we can multiply again by the reciprocal of that, and we can, we'll combine like terms first in the exponent on the temperatures. So then T2 over T1 to the CV plus R over CV is equal to pressure 1 over pressure 2 to the R CV and then plus CV up there. And then we can multiply by the reciprocal of these again and just get temperature 2 over temperature 1 is equal P1 over P2. And then we'll be multiplying this by CV over CV plus R, so then this will cancel out up here. And then those will just cancel out up there. Actually, I believe this is still negative. So then what we get is the exponents will multiply down, so then it just becomes negative R over CV plus R. And from there, we can take this second equation and put it into the one from video 1, and we can derive the expression for adiabatic reversibility for the ideal gas if we take it from pressure 1 to pressure 2.